Hello guys, thank you so much for being with me in another machine learning tutorial video. In the previous video, we talked about the kernel function and the related tricks. Today we discuss the main issue in machine learning, which is the determination of hyperparameters in order to better clarify the discussion of replacing the dot multiplication of functions in the kernel trick. I will examine an example. We want to give an example of a polynomial kernel of degree q. Now consider this q to be 2. For simplicity, consider the problem in two-dimensional space. We consider the polynomial kernel in terms of the dot multiplication of two vectors. We have already said that dot multiplication is directly related to the similarity of two vectors. So this kernel function must have two features. One is that these two vectors should return a high value for this kernel function if they are very similar, and vice versa, and they should also have the ability to move. We have considered two data. We can solve the problem in this two-dimensional space, and we can also map these data to the six-dimensional space and then solve the problem. First, we solve the problem in a very simple way. We calculate the dot multiplication of two vectors and add them to 1, and then raise the result to the second power. In this way, we performed all calculations in the same two-dimensional space. Now, once again, we get help from the kernel function. We map x and y to the higher space and then do the calculations. We define a fix and we define fi(x) and fi(y) in this way inside the Python files, which is not opened now on my system, because we want their dot multiplication to be equal to the expression on the left side of the image. In this order, we have 6 features. Now we multiply these two together internally. We need to reach the expression on the left. Pay attention that x and y did not have two more features each, but now fi(x) and fi(y) have 6 features. Each of them actually has 6 features. That is, we have mapped the problem to a 6-dimensional space. So we have two ways to calculate the similarity we want. One is to solve the problem in two-dimensional space, and one is to solve the problem in 6-dimensional space. The kernel trick says that we don't need fi(x) and fi(y) anywhere, and all we need is the dot multiplication of these two. Now let's see which one is more efficient. Note that here the data is small and the number of dimensions is also small. In the real world, where the examples are larger and the dimensions are higher, the differences will be more significant. We calculate how many multiplications and additions we need in both methods. In the normal way that calculations are done in two-dimensional space, we need 3 multiplications. If we solve the problem in 6-dimensional space, we need 6 multiplication operations. Likewise, the number of addition or subtraction in the first method is 2 and the second method is 5. Once we calculate this in computer, we don't need to do all the calculations, because when we perform multiplication operation of two variables once, the compiler itself stores this value and does not perform the multiplication operation again. For this reason, it is better to use the kernel. In this video, we want to determine the hyperparameters. We have said that SVM is a very popular method, especially among non-expert users. We have already seen the Gaussian kernel formula, and we said that the bigger the sigma, the smoother the kernel, and the smaller it is, the sharper the kernel. I already explained that the number this kernel returns is between 0 and 1. If the similarity is maximum, it returns a number of 1, and if the similarity is too low, and the 2 points are too far apart, it returns a number close to 0. Determining the sigma and in general these hyperparameters is our discussion now. We present this discussion in SVM, but it can be extended to all areas of machine learning. In this video, we want to review cross-validation methods. This is the form of Gaussian kernel function used here. The figure inside the Python files is similar to the normal distribution function. The figure of Gaussian function actually is similar to the normal distribution function, except that in the Gaussian function the area under the graph is not 1 because the coefficient has been removed in this in the figure of Gaussian function. You can see the obtained decision boundary along with the margins. I said that this method tries to maximize these margins. The data I circled in the Python files are the support vectors. This is the kernel, the Gaussian kernel, which I explained and draw in the Python files. You can see that it has separated the data well, has a suitable margin and a good generalization capability. So we have a series of hyperparameters. Suppose we want to know the value of the hyperparameter C in the soft margin method. We always divide the entire training data into two categories. We allocate a larger part to training and a small percentage of the training set to testing. The purpose of the training set is to determine the value of the parameters parameters like b and theta or b and w's, and the purpose of the test set is to estimate the generalization accuracy. Now we can consider this hyperparameter C as a fixed value, for example 10. If this value is correct, it should perform well on the test set. This is a very bad idea because the only time to use the test data is in the last stage, and before that you should not use this set at all. So the data can be divided into 3 parts. We leave the test data until the last stage and do not use them before that. We will divide the training set again into 2 parts. We use a large part for testing and some for validation. The purpose of this validation set is to set and determine the hyperparameter values. We use a large part for training and some for validation. Okay, but this is a better thing. The method I want to do is k-fold cross-validation. In this method, we divide the training data into k-equal parts. The value 5 and 10 are common values of k. Now, how do we use this k part? We train the classifier k times. Of course, this method is not limited to classification, and the problems can also be regression. At each training time, we allocate 1 part of this k parts to validation and use the rest for training. That is, in each training session, a different session is dedicated to validation. That is, at each training time, 1 part is dedicated to validation and k minus 1 part is dedicated to training. We record the accuracy of each validation. Finally, we take the average between these precisions, accuracies actually. Finally, a number is obtained which is a good estimate, and now we consider C equal to a different value, say for example 15, and perform the validation again. As a result, we compare the accuracies and choose the best hyperparameter. In the previous videos, we suggested two more suitable solutions when the problem occurs, one of which was regularization, and here we also explained the model selection method. I explained the implementations with the help of scikit-learn library facilities. There are different classes in this library, such as K-fold and stratified K-fold. We have used the latter here. If we do shuffle, the data will be cut first and then divided into k-parts. This improves the result. Therefore, it is better to always set this argument to true. The higher the value of k, the more time consuming the algorithm is and the higher the accuracy. In the second step, you should specify a range for the hyperparameter you have. Here we have two hyperparameters, one C, which is actually important to the error. Large C means that we attach great importance to the classification error, and small c means that we prefer to have a larger margin. Here gamma is equal to -1 divided by twice the square of sigma. That is this gamma, which is considered in the scikit-learn library, has an inverse relationship with the sigma that we considered. Here for C, we have considered a range from 10 in the power of -3 to 10 to the power of 5, positive 5. The number of numbers will be 9. Here we have used the log space. Okay, it means that every number is the product of the previous number in 10. The more numbers we consider for these hyperparameters, the more calculations will be made, but it doesn't have to be like that all the time. In the next step, we want to use the SVM algorithm. This algorithm has two hyperparameters in the scikit-learn library, so we consider a dictionary for these hyperparameters in Python. For now, we are focusing on two hyperparameters, and now we can use the grid search CV method. This is an SVM. Its first argument is the classifier, the second argument is the hyperparameters, the third argument is the same as a k. After doing all of these steps, we apply the fit function. This step of applying the fit function is common to all machine learning algorithms. I have put the implementations in the files for you. I emphasize again that you must solve the exercises and start the implementations in the Python files. For the implementation, we also said that we do not implement it ourselves and use the existing packages. If n is much larger than m, we use a linear kernel, and if m is much larger than n, we use Gaussian kernel. Let's have a comparison between the methods that we have said so far. If the number of features is very large and the number of data is small, we prefer to use logistic regression or linear support vector machine. But in the opposite case, we prefer to use SVM with Gaussian kernel. In both cases, neural networks can be used, but it may take more time and be harder to teach, to learn, actually to train. Because a hyper parameter has more because there would be more hyperparameters, and this will increase the difficulties. Finally, I have provided you with this link, with a link in the Python files to practice more and more. Okay, I transfer the rest of the concepts for next videos. I again highly recommend you not to miss the upcoming lectures, since they contains lots of practical and important tips, and can help you to become an expert machine learning engineer. Have a nice time.